So now for our maximum and minimum values. Let's begin by defining local and absolute maximum and minimum values. We're going to let C be a number in the domain D of a function f. Then f of C is the absolute maximum value of f on D if f of C is greater than or equal to f of x for all x in D. We've got an absolute minimum value of f on D if f of C is less than or equal to f of x for all x in D. So what does this really mean? So absolute maximum occurs if f of C, well, when I say f of something, this is talking about the y value. We know y is the same as f of x. So we're saying here that the y value is greater than or equal to all of the other y values at an absolute maximum. So I'm looking for the largest y value, and I see that right here. So right here, I've got an absolute maximum. An absolute minimum occurs where the y value is less than or equal to all the other y values for x in the domain. So it's the smallest y value, and so I see that right here. This is my absolute minimum. And again, we're talking about these y values. And the maximum and minimum values are sometimes called the extreme values of f. The extreme values. And sometimes you'll see this word extrema. This is just the plural of extreme. So if you're looking for the extrema, you're looking for those maximum and minimum values. So now for the local maximum and minimum values. So we have our absolutes. So our absolute max is the absolute largest y value on a certain interval. Absolute min is the absolute smallest y value on a certain interval. But now we have this local maximum and local minimum value. We've got a local max if f of C is greater than or equal to f of x where x is near C. So now this doesn't necessarily have to be the largest y value on the interval. It just has to be the largest y value over a certain region. So if I look at this first peak right here, can I see that maybe this point right here, this has the largest y value over this small interval. And so this is a local maximum value. This is a local, and I'm just going to abbreviate that, max. Okay? Now I've got this other peak. Now what about this right here? Well, now this is not just the local max, but in fact it looks like the largest y value on the entire interval. And so this is an absolute max value. This is an absolute maximum. All right, f of x is a local minimum value if f of C is less than or equal to f of x where x is near C. So now let's look at our minimum values. So I'm looking for my valleys. Right here at this point, can I see that my y value is smaller here than it is to the left or to the right of this point? And so this is a local min. Okay, I've got two other points that are fairly low in comparison to the others. Now this is an endpoint. Endpoints cannot be local maxima or minima, but they can be extreme maxima or minima. So they can be those absolute or global maxima or minima. We've got different words for that. So this right here looks like an absolute min. It looks like the smallest y value on this entire interval. So this looks like an absolute min. And so that will leave me with this valley right here being a local min. Okay, now this endpoint right here, it's not going to be a local max or min because we said endpoints can't be local maxima or minima. It's also not an absolute maximum or minimum value here because this point is slightly higher. This has a larger y value than this point right here. So this endpoint is actually insignificant. All right. So now we will look at the derivatives of these local extreme maxima and minima. We will use a similar function as above, but now it will be continuous on negative infinity to positive infinity. So all that means, if I look at these two graphs, the only difference is that my endpoints have now turned to arrows. So now these functions are continuing from the left and right. So I'm not worried about the endpoints at all. I've got no endpoints. And so now what I'm going to do with this is I'm going to look at the derivatives of the local and extreme maxima and minima. So let's just put points where all of our local and extreme maxima and minima are. We're just going to exclude that endpoint because now we have no endpoints. So local max here, local min here, local, well, at an absolute max, and a local min here. All right, so I've got my first 4 points here, so my extrema from above. So now what about the derivative of these points? Well, I remember that the derivative is the slope of the tangent line. If I were to draw a tangent line right at this point, can I see, okay, I'm looking at my slope, positive, positive, positive. My slope would be 0 right up here before being negative again. So my tangent line at that point would be horizontal. What about up here? Well, in the same way, at that peak, my tangent line would also be horizontal. At this valley, at this local minimum down here, tangent line would also be horizontal. At all 3 of these points, would we agree that my derivative is equal to 0? I know a horizontal tangent line has a slope of 0. So here, here, and here, f prime of x is equal to 0. What happens right here, though? Does anyone remember the derivative at a point? Well, at a point, my derivative does not exist. So I'm going to say f prime of x does not exist here. All right, and we talked about the idea before when we have local maxima and minima, the derivative is going to be 0. So we've already discussed this. To find potential maxima or minima, what we're going to do is we're first going to find the critical numbers, which are x values such that f prime of x is equal to 0 or f prime of x doesn't exist. So we're going to find where the derivative is either equal to 0 or the derivative does not exist. Now, if f prime of c is equal to 0, is there always a local minimum or maximum at c? So I have kind of shown that wherever I have a local max or min, either the derivative is equal to 0 or it doesn't exist. But is the converse always true? Let's look at an example. Let's look at f of x equals x cubed. Let's look at this function. So let me graph this really quickly. Okay, so I want to graph x cubed. Now let me start off in a standard window. And so this is my function. If I want to get a better idea of what's happening at the origin, I can zoom in. And let me zoom in near the origin. So I can see what happens to this curve. It almost looks like my curve disappears, but it really just lines up with this x-axis. So this is what x cubed is going to look like. All right, let's get a rough sketch of this. All right, something like this. Now what happens at the origin? Right here. Well, I can find the slope of the origin. right? Because I can find the derivative of f of x. F prime of x is equal to 3x squared. And then at that c value of c equals 0, let's see what happens when f prime of 0. This is where x is equal to 0. So this is going to be the slope at my origin. Well, this is just 3 times 0 squared, which is 0. And so what this tells me is that I've got a horizontal tangent line at x equals 0. So I have a horizontal tangent line right here. So in this case, f prime of 0 is 0, but is this value a local max or min? Well, no, not a local min, because I've got a bunch of values to the left that are smaller than this point. It's not a local max. I've got a bunch of values to the right that are larger. And so I've found that right here, f prime of 0 equals 0, but x equals 0 is not a local max or min. And so our answer is no. So the converse is not always true. So we can confirm that if something is a local max or min, the derivative is 0 or it doesn't exist. But just because the derivative is equal to 0 does not necessarily mean that this is a local max or min. So these are what's called critical numbers, and we're still going to need to test these critical numbers to make sure they're truly maxima or minima. Okay, now what we're going to be doing for most of today is we're going to be finding the absolute maximum or minimum values of a continuous function f on a closed interval from a to b. So what this means is that we've got solid endpoints. This is what it looks like in the first graph, where we've got these solid endpoints. Okay, so what we're going to do is we're going to find all of these critical numbers or critical values of f in the open interval from a to b, so excluding our endpoints. So we're going to find the critical numbers, which, remember, is where f prime of x is equal to 0 or f prime of x does not exist. And then we're going to plug all the critical numbers, only the critical numbers that are in the interval, because we're looking for the absolute extrema on a closed interval, as well as the endpoints. Always going to test the endpoints into the original function to find the largest and smallest value. Whatever the largest value is, that's our absolute max on the interval. Smallest value is our absolute min. Okay. So in question 1, let's find the absolute maximum and minimum values of the function on the given interval. So we've got f of x equals x cubed plus 6x squared minus 36x. So step 1, we want to find all critical numbers. And so to do this, I want to start by finding the derivative of f of x. The derivative, f prime of x, is going to be equal to 3x squared plus 12x minus 36. So just using that power rule for all three terms. And now I know a critical number is where the derivative is equal to 0 or the derivative does not exist. When I'm saying the derivative does not exist, the things I'm looking for are zeros in the denominator, negatives inside of an even root, or 0 or negatives inside of logarithm function. So I don't see anything that's going to make this not exist, and so I can simply set this derivative equal to 0 to find all of those critical numbers. Okay, now I see a quadratic on the right-hand side, and so I'm going to factor this. The first thing I'm going to do though to make it easier to factor is I can see that I can pull out a 3 out of all of these terms. And so let me pull out that 3. I'm left with x squared plus 4x minus 12. And now I can factor that quadratic on the right a little bit more easily. I know my first value in both factors is going to be x, and then I'm looking for two numbers that multiply to give me negative 12 and add to give me positive 4, and those two numbers are going to be positive 6 and negative 2. All right, and now I'm just setting both of these equal to 0. The 3 doesn't really mean anything because if I set up the equation 0 equals 3, I know that's not true. So the 3 can just kind of get left out at this point. And so I've got x plus 6 is equal to 0 and x minus 2 is equal to 0. Bringing that 6 and 2 to the other side, I get x equals negative 6 and x equals positive 2. All right, so these are my two critical numbers. Now, step 2 is to test all critical numbers in the interval. So my open interval in this case is going to be negative 4 to 3 with parentheses because I'm testing the endpoints anyway. So I'm testing all critical numbers in this open interval and the endpoints. Okay, and I am plugging all of these into my original function f of x. So critical numbers in the interval. So x equals 2, yes, it's in my interval. X equals negative 6, no, we do not want to test this because negative 6 is not in the interval from negative 4 to 3. If I test the point x equals negative 6, I might get an absolute max or min that I don't want. I might get that there's a larger or smaller y value than any others outside of this interval, but I'm only worried about what's inside of this interval. And so I'm going to test x equals 2. I'm going to test, and now my two endpoints, x equals negative 4 and x equals 3. And I want to plug these into my original function f of x. And so f of x, when I plug in 2, this is going to give me 2 cubed plus 6 times 2 squared minus 36 times 2. And now don't be afraid to do this in your calculator. So I can put in my y equals, this is probably the quickest way to go about it, x cubed plus 6x squared minus 36x. And then what I can do is I can go to my table. I can make sure I am in, if I go to second window, my table settings, I'm going to make sure I'm in ask for my independent variable. And so now, trying to go back to my table, and so now I'm just going to put in all the x values that I'm looking for. I'm looking for the y value at x equals 2. I found that to be negative 40. I'm looking for the y value at x equals negative 4, 176, and the y value at x equals 3, negative 27. So f of 2, negative 40. F of negative 4 is 176, and f of 3 is negative 27. Okay, now my max and my min. So remember that the max and min talk about those y values. So my max is going to be the largest y value or output, and so my max is 176. My min is that smallest y value, and so my min is negative 40. And I can also check this in the graph of my calculator just to be sure. So if I go to, now this is me going to a standard window. So this is a standard window with that function. And it's a little bit difficult to see, but what I'm looking for is I'm looking for the window that only includes x values from negative 4 to 3. So I'm going to adjust my window as x goes from negative 4 to 3. And then my y scale, so I've actually got my y min and y max. So I should see that y goes from negative 40 to 176. Okay. All right. And I can see that right here looks like it's my minimum. If I go to second trace and trace that value, I saw that that happened at x equals 2. Yes, I can see that y is negative 40, so that's my minimum. And then I saw that my maximum occurred at that endpoint of x equals negative 4. Well, let's try that again. Of x equals, let's trace that value, negative 4. Yes, right up here, that's my max on the interval. So I can just confirm that graphically as well. So while you can use your calculator for this evaluation at each of these x values, just make sure that by hand you show how we found those critical numbers.